Welcome to our regression lecture on multiple regression. Simple linear regression is what we just finished, and that explored how the mean for a quantitative response changes with differing values of a quantitative explanatory variable. For instance, we were working with this data set on predicting deadlift personal records from bench press personal records. And we fitted a straight line through to explain the relationship, and we use that line to make predictions of our response variable y, or deadlift. And when we did simple linear regression, we used the following model. We had our y, which is the thing we were trying to predict, our intercept beta naught, our slope beta 1 times our predictor variable x, plus some error. And the errors we assumed were normally distributed with a mean 0, constant error variance, and the errors were independent of one another. And of course, this line, beta naught plus beta 1x, if you want to think of it like the population line that goes through the population of all deadlift and bench press personal records, is the mean of the y's at the given x value. Multiple linear regression is a natural extension of simple linear regression. We have our y that we're trying to predict. It's quantitative. We've got an intercept in our model. We've got the errors again, but this time the middle part looks a little bit different. Instead of just one x predictor, we have multiple x predictors. And so we have a coefficient, a beta coefficient for each of those predictors. Beta 1, beta 2, all the way up through beta k. Again, we're going to assume the errors are normally distributed. They have mean 0, constant variance, and the errors are independent of one another. So before, when we had one slope, one predictor, we had a line, and we could picture that. Now if we have two, we might have a plane, etc. So it's a little bit more difficult to picture, but we can always go back to the base model of simple linear regression and think about the properties in relation to that one so we can picture it. So we're going to be working with a data set from Zillow, and this is from the Zillow website. Zillow is the leading real estate and rental marketplace dedicated to empowering consumers with data, inspiration, and knowledge around the place they call home and connecting them with the best local professionals who can help. So Zillow is kind of famous for their Z-estimate. The Z-estimate is their home valuation tool where they estimate the market value using a proprietary formula, and you can look up your home address and see what the Z-estimate is, what it would go for according to Zillow. Now this is not perfect, but Zillow is constantly trying to update their algorithm. In fact, right now they have a contest on Kaggle offering $1.2 million for the team that comes up with the best prediction algorithm. So anyway, they're always trying to update. Now, one method that we could use to estimate home values like Z-estimate is multiple regression. So we're going to work with this data set that has 1,057 home sales in upstate New York and the region around the city of Saratoga Springs. We've got sales price that we're trying to predict in dollars in 2002. Living area in square feet, number of bedrooms, number of bathrooms, fireplace, and the age in years. So the first thing to do is take a look at your data, get a feel for what the columns are called, what it looks like. This is what your data set looks like. You can download it from Canvas. It's contained in the same little part of the module with your lecture notes. And the first thing that we want to do is do some exploratory data analysis. So let's take a look at sales price on living area against living area. It does look like it has a positive relationship. As living area increases, sales price increases. And we do have some points that look like they would have a high residuals if we were to fit a simple linear regression, but these are home prices. We know there is some variability that we're going to have to account for here. And if we look at sales price versus bedrooms, we can see that it looks like as the number of bedrooms increases, sales price might increase as well. So I'm just going to go ahead and start right off by fitting a multiple regression using living area and bedrooms as my predictors. So the first thing I do is in R, I'm going to attach the data set that I called in to R called Zillow. And doing that will allow us to not have to type Zillow $ when we're calling in columns. Now we can just refer to the column names just as they're named. So if you take a look at your data set in R, you'll see that living area is named living dot area. Bedrooms is called bedrooms. So I'm going to call my fitted model fit. I'm going to use the LM call just like I did in simple linear regression. Do my Y tilde my X's. So tilde living area plus bedrooms. The next couple lines of code are the way that we always have plotted our residuals versus predicted plot and our QQ plot of the residuals. But notice this win.graph call. That's going to open up a new graphics window so you don't overwrite your residuals plot, and you can have your residuals plot and your QQ plot of the residuals right next to each other. However, win.graph only works on a Windows machine. So I think that in a Mac, if you want to do this, I think you can use Quartz there. If it doesn't work, you can always save a copy of your graph into Word or something before you overwrite it with your QQ plot. And of course, the summary fit call gives us our output that we're used to seeing. Now, this output is exactly identical to the output from simple linear regression, except that now for our estimates, we estimate our intercept and we estimate the coefficients for each of our two predictors. So let's practice stating the regression equation. Same game we played with simple linear regression. We've got our B naught, which is $20,986.09. We've got 93.84 times living area minus 7483.1 times bedrooms. So the estimated price hat, is 20,986.09 plus 93.84 times living area minus 7483.10 times bedrooms. And we can use this equation to make predictions. We can predict the price for a 3-bedroom house with 2,500 square feet. So we start with our regression equation that we just wrote, and we plug in 2,500 for living area and 3 for bedrooms. And we get $233,136.79. So the estimated selling price for a home that's 2,500 square feet and has 3 bedrooms is $233,136.79. So the same way that we made predictions before. And a residual, we need to talk about the variability about those predictions. So we need to talk about residuals. A residual is defined in the usual way. A residual is y minus y hat. That is the observed y minus the fitted y. So if your y is above your modeled y, your y hat, then you have a positive residual. And if it's below it, you have a negative residual. Knowing this, the standard deviation for the residuals, the standard error of the regression, is also defined in the usual way. Now, remember that degrees of freedom for simple linear regression were n minus 2, and that's because you were estimating your intercept, beta naught, and your one coefficient for your slope, beta 1. So 2 degrees of freedom. 2 were docked from the degrees of freedom. For multiple regression, you can have more than one predictor. So we just update our formula to be n minus k minus 1, where k is the number of predictors. So in our case, in our example, we have 2 predictors. So our degrees of freedom are going to be n minus 3. And then the standard error is defined in the same way that it was before. So it's the square root of, I forgot my summation, so it's the sum of those residuals squared divided by the degrees of freedom and then square rooted. So it's defined the exact same way that it was in simple linear regression. And of course, we're going to let R calculate it for us. So let's find and interpret the standard error of this regression. It's right here. It's $50,140. And how do we interpret that? Well, that's the variability around the model. And what is the model? That's where our predictions are. So, and we're predicting Y, which here is sales price. So predictions of sales price tend to be off by $50,140 in general using this model. So the same interpretation that it had in simple linear regression. There's nothing new there. And of course, we can talk about r squared. Now notice that we have the one that we looked at before in simple linear regression is about 0.58. And the adjusted r squared, which we'll be teaching you in a little bit, is also 0.58. So how do we interpret r squared? Well, remember that's the fraction of the variability in the y's that's explained using this set of predictors in this regression. What's our y? Sales price. So 58% of the variability in home price is explained using living area and bedrooms in this regression. Again, same game that we played in simple linear regression. So this looks a lot like simple linear regression so far, but interpretations of our coefficients are going to change in a subtle but important way. Also, the relationship among predictors can complicate the analysis, and determining the best set of predictors is not always straightforward. We had 5 possible predictors in our Zillow data set, and I picked 2 of them to run our first regression, but we could have picked other combinations. We could have picked some combination of 3 of those predictors. And sometimes it's not always straightforward how to pick the best set. So let's start by doing something that's changed a little bit with multiple regression. Let's interpret the coefficient for living area. So first, let's find the coefficient for living area. It's right here in our coefficients output. So the estimate for that is 93.842. All right, so if this was simple linear regression, how would we interpret that? We would say for a 1 square foot increase in living area, we expect sales price to increase by $93.84, right? So how does it change for multiple regression? Only by a little bit. We just have to add after we accounted for bedrooms in the model. So after accounting for number of bedrooms, then you go on with your same interpretation that you had in simple linear regression. We expect sales price to increase by $93.84 for each additional square foot of living space. So again, the only new thing is that you have to add the part about accounting for or holding the other variables constant. We'll be able to picture that a little bit better in just a minute, what I mean by that. All right, so let's play the same game and interpret the coefficient for bedrooms. All right, so here is the coefficient for bedrooms. So if it was simple linear regression, we would say that for each additional bedroom, we expect sales price to decrease, that's why the negative sign is on there, to decrease by $7,483.10. But it's multiple regression, so we have to say after we've accounted for living area or holding living area constant. So holding square footage constant, we expect sales price to decrease by $7,483.10 for each additional bedroom. Now this might seem counterintuitive because in our scatter plot we saw that sales price increased with bedrooms, and now it's saying it decreased. So we'll talk about that in just a second. All right, so why is this coefficient negative? We saw that our scatter plot looked like a positive relationship, and I went ahead and fitted it with a regression, and it is a positive slope that is significant. We have a very low p-value on it. And I calculated the correlation of bedrooms with living area, and it's 0.66, so positive, a moderate correlation there. What's going on here is living area and number of bedrooms are related. We're going to talk more on that concept later. That's called collinearity. But the key point that we want to emphasize now is that multiple regression coefficients must always be interpreted in terms of the other predictors. So think about our example. If you have 2 homes that have the same square footage, maybe 1,000 square feet, and one of them is 2 bedrooms and the other one is 7 bedrooms, can you picture the difference for a home buyer coming into a home that has 2 bedrooms in a space and another home that has 7 bedrooms in the same space? It might be that more bedrooms in that same size space seem cramped. They're smaller, and it drives down the price. So just remember that multiple regression coefficients always have to be interpreted in terms of the other predictors, because in terms of the other predictors, after you account for the other predictors, it might have a different kind of a relationship than it would just by itself. Also, be sure that you don't imply causation. Just because variables are related does not mean that one causes the change in the other. Think about the example of snake bites and ice cream. They're highly correlated. As snake bites increase, so do ice cream sales. But does that mean that one causes the increase in the other? No. There's something else going there, which is summer. All right, so other factors besides the ones that are in our model could be at play, causing the increase or decrease in our response variable. This model simply reports the relationship between the number of bedrooms, living area, and price.